So let me talk about test 3 for a second as waiting for people to come in, which is test 3 will start with 3.11, since that's the last thing that was not on test 2, and then go through chapter 4. So 4.1 through 4.7, although 4.1, remember, is kind of an intro, so there isn't really anything there by itself. And 4.7, I'm not sure if that's going to be on it or not. So there will definitely be section 3.11, and I'll write this tomorrow when I'm more sure exactly what's on it. But it will definitely have 3.11, definitely have 4.2 to 4.6, and then we'll see about 4.7. And that is, again, Monday, the base one. So the next few classes, today we will really do 4.5, which I talked about quickly yesterday, but we didn't get to anything. And we'll also start 4.6. Tomorrow, again, we'll have new material, so continue 4.6 probably, do a couple examples from 4.5 and 4.6, and then get into 4.7. Thursday is the last day of class, so we won't do anything new, just go over questions you have on the review. And the review is on Blackboard, and today, tomorrow, depending on when I have time, I'll write up and put up the answers. Right, so today, so first, same as yesterday, I haven't figured out how to make the writing thinner, so it's going to be a bit messy again. But so we'll start off with homework, and we've sort of already done some of the homework, so there isn't too much. So let me look at one from 4.4. That's a y. Making it look like determinants. So we have the points 1, 5, 3, 5, and 1, 11. So not the scale, but 1, 5, 1, 11, 3, 5. And it says we're going clockwise. Counterclockwise, sorry, because I'm drawing it. And we want to find the line integral on the surface. So the first thing is, since it's closed, and since we're going to use this anyway, we probably should check to see if it's conservative. So is this conservative? And similar question, how do I check? So is this conservative? No, because we're going to compare QX to PY. Since the section is Green's theorem, probably not a bad idea to just do the two-dimensional curl. So QX minus PY is minus 3 minus 5. So it's not 0, so it's not conservative. If it was conservative, so if that was 0, we would be done, because what would be the integral? 0, right? Because if the vector field or force field is conservative, then if we go over on a closed path, then we get 0. I should say, I don't think I wrote the full thing. When I say a closed path, officially you need to have a closed simple path. So it gets a little weird if, say, I had a path like that. it still might work, but it's just now a bit more complicated. So in Green's theorem, we're talking about a simple closed path. So nothing that crosses over or anything like that. Okay, so on the other hand, you can see that this is a fairly simple function. So here's what we want to get, and we want to do the integral, the line integral on C. And by Green's theorem, we get the double integral of R, which is the space that's enclosed by the closed curve. And as I said, we might as well do this because now we're integrating that. And this is simple because q of x minus p of y is -8. So I don't actually have to do the integral. I get -8 times what? Right. I was looking for the more general thing, which is the area of R, but you're getting it. Giving me the next one. So it's going to be -8 times the area of the triangle, which is 1/2, times the base, which is 2, times the height, which is 6. So therefore, -48. So Green's theorem works as it's closed. If you have a fairly lengthy path or the function is not very nice, this is an alternate even if it's not closed, because what you can do is add a segment that will close it, use Green's theorem, and just look at that one segment using the method from 4.2. Obviously, if it's conservative, you don't do that because conservative is easier. But so any questions on this? This is the basic Green's theorem. Should mention, many of the ones we do are ones where we don't actually have to do the integral, but there's no reason we can't get one where you have to do the integral. So if the q of x minus py is -8x, then we would have to actually do the integral because that's not a constant. So we're going to get a typical double integral going back to chapter 3. So we did a couple of these also yesterday, so that's the only one I wanted to look at for today. But any other ones from section 4.4 that you want to look at? No? Okay. So again, just the recap, which is 4.2, 4.3, and 4.4 are all looking at line integrals. 4.2 is the basic method, which always works, but might not be easy. 4.3 is if the vector field is conservative, in which case all we care about the endpoints, where we have to get the potential function, which is the equivalent of an antiderivative, and then plug in the endpoints. And Green's theorem says if we have a closed path, we can make the line integral into a more typical double integral over a region. And now we're going to do something similar. So we started very quickly, but I don't think, you'll tell me in a second, I don't think we actually did an example of the flux. So 4.5 is the basic flux. So again, method that always works. And then 4, 6, and 7 are cases where you can do it other ways. 4.6 is kind of an extension type thing of Green's theorem, and 4.7 is showing that we can switch what we're looking at, which I'll explain when we get to it. 4.5 is flux, which is just another word for flow. So again, in the background, what I think when I'm thinking of these integrals, although it doesn't always make sense, is we have something like a river, so a three-dimensional thing, and we want to know how much water flows through a imaginary dam. So how much water flows through a two-dimensional surface. And that's represented by this. Officially, the b is a vector also, but if I put the line above it as I usually do for a vector, it starts looking like a gradient. So I don't want to do that. So I'll leave it without it. But the b is, the capital V there is a vector. And so v is the vector field, which often in this case is velocity, right? The velocity of the points of water, and is the normal to the surface M. And so we do something similar to the line integrals, which is we parameterize the surface M, which I'll write after I write the integral. In this case, since it's a two-dimensional surface, we need two variables. And then we take the dot product with the normal. And the way we get the normal is by looking at the cross product of the two tangent vectors, because those will be parallel to the surface. Therefore, the cross product will be normal to the surface. In general, then, we have to be a little bit careful, because we're going to be wanting the flow in one direction. So if we just take the cross product, we get a normal vector, and we just might have to check to see if we have the one we want. So I do an example. As I said, I don't think we did one yesterday. Might as well ask, did we do one yesterday? I think this is as far as we got yesterday, right? So yeah, we didn't get one. So let's start one, and I think I was going to start writing here, but I think I'm going to put it onto the next page so I can maybe fit it all on one. So there's my velocity field. As I said, if I'm now thinking if this is river, this doesn't really make sense as a velocity field, but so kind of a mixed thing. That's the word surface. And similar to what we did in 4.2, I'm going to start with one where I just give you the parameterization, and we'll go from there. So the surface is this thing, and I don't really have a good image of what that looks like, but it's some two-dimensional surface in 3 dimensions, and I want to see how much water flows through that. So the vector field, the velocity field here is kind of weird one. I have no idea what that would look like, And I don't really know what the surface looks like, but so when I'm trying to imagine water flow through something doesn't really get, but let's follow through the steps. So steps are, I need to get the normal vector, which I do by taking the two partial derivatives. So derivative of r with respect to u, which is 1 and v and 0. Derivative with respect to v, so 0 and u and 2v. Then get the normal vector, which is the usual, the ijk. And so I can fit it in, I'll just give, and you should be double checking me here as usual. 2v squared minus 2v and u. So in this one, since I'm just making it up, I can't really check to see if that's the normal I want because, as I said, it could be the one in the opposite direction. So it could be instead the negative 2v squared positive 2v negative u. On a problem like this, I would have to tell you because you can't really picture what's going on. So let's just pretend that's the one we want. So it's our normal vector at any point uv. Then we plug the parameterization into the vector or velocity field. So plug in x equals u. And then y, which is uv. And then 2 times x times y times z. So 2 times x times y times z. And then over the range of un v, the dot product of those two things. Remember what this is shorthand for, because we've simplified something out, is what we want to do is multiply the flow in the direction perpendicular to our surface times a surface area. And so that's why we do this dot product. This is, the first one is v in general. When we take the dot product with the normal, we get the part of the velocity field that is perpendicular to the surface. Officially, we need the normal vector to be a unit vector. So really, we should be dividing by the length of that vector. And then we want to multiply by the surface area of a little piece. But the surface area is the length of the cross product, which is also what we would divide by the normal vector to make it into a unit vector. So we have the length of the cross product in the denominator and the numerator, so those cancel out. So we see part of what's going on, which is this part is the part of the velocity field in the direction of the normal, so perpendicular to the force field, that velocity field. But then we lose off the piece that we're then multiplying that by the surface area of the little piece we're going through. And then from there, you can see this one is now fairly easy. We would get the 2u squared v squared minus 2u squared plus 2u cubed v cubed, which is a pretty easy integral. So this is kind of the full one, except in a more general one, you might have to get the parameterization yourself. So here's the basic thing. Any questions on this? Okay, so let me do another one. One where, in some ways, you can see what's going on a little bit better. In this one, since we can picture, I can actually talk about the orientation. So here we have the disk x squared plus y squared is less than or equal to 25, which is just parallel to the xy plane at z equals 3. So here you can see we can either be going through the surface, up through the surface, or down through the surface. And obviously, the flow in one direction will be the negative of the flow in the other direction. Okay. So in some ways, what we would want to do is parameterize this thing. But before I do, and I'll actually do that later, show if you didn't do it, let me ask, what is the normal vector to the disk? And this you should be able to do without doing the cross product like we did alone. Because we have a flat surface, so unlike the last one where the normal is changing depending on where we look, since this is flat, the normal vector is going to be the same everywhere on the surface. And here, since it is parallel to the xy plane, what is the normal vector? Does anyone see it? So basically, yeah, in the z direction, which means is given by that, right? And so this is where the up comes, because if we were oriented down, it would be 0, 0, negative 1. So on flat surface, like this one, so here what we have is, so there's the x, y, and z. And I can't draw it very well, but we have the picture of our disk. And it is parallel to the xy plane. And so we want something that's perpendicular to that. And you can see sort of by design that is straight up. So picture the disk as parallel to the disk if you're working at a desk right now. And you can just see, well, if I draw something perpendicular, I can just stick my pencil on it it'll be pointing straight up, which is in the z direction, which means it is the 0, 0, 1. On the other hand, if it was x squared, let me ask while I'm doing this, suppose it was x squared plus z squared is less than or equal to 25 when y is equal to 3. So if I switch the y to z in the circle, I'm not going to write because I don't want to mess it up, then in that case, what would be the normal vector? Right, 0, 1, 0, because now y isn't there, so it's parallel to the xz plane, and therefore it's in the y direction. So let's start the parameterization. I'll fill this in. But you'll tell me why we don't need the full thing. So here's x, here's y, and then we have z. So let's start off with z. What is the parameterization for z? Here's our surface, 3. We know from the last one that in the next step, what we're going to do is take the dot product of these two. So do I really need any other part of the parameterization? Does it matter what goes into these two? No, because I'm going to multiply by 0, right? So here you can see this becomes simple because I don't really need to do the parameterization except for the really basic part, z is equal to 3. And in a similar way, that means when I do this, actually this is where I don't really need anything there. So actually I was getting ahead of myself. The reason we only need the third one is because the only component we need is that one, which only depends on z. Because this, sorry, I said that badly because this is x and y and z. So we don't need the parameterization except for z equals 3. As I said, I'll fill that in a second. But therefore, we're doing the integral over the disk of the dot product of this thing, the something something 9, and the 0, 0, 1 dA. Since that's a constant, 9, I don't have to do the integral. And I'm integrating over the disk. So therefore, what am I going to multiply by? The area of the disk, right? Which is just the pi r squared. And r we can see is 5. So if we have a flat surface, things get easier because we can often just read off the normal vector, which means we don't necessarily have to do a full parameterization. But let's put it in, because maybe it will come up later. So we're doing a disk, which means what type of coordinate system are we going to use? Polar. The difference here to our regular one is we don't have a fixed r. So we can use the r cosine, but then I'd have to rewrite this. Instead of uv, it's r and theta. So I'm just going to do the u cosine of v, u sine of v. But there's no reason we couldn't have done parameterization r of r and theta, and then do the usual r cosine v, r sine v, where u goes from 0 to 5, the origin to the outer circle, and v goes from 0 to 2 pi, because we're doing the full disk. So we could do it using the full thing, we just don't have to. this, if this was flow of water, that would then be a volume, how much water goes through in a certain amount of time, which is sort of in the background there. So this one, you can kind of see a bit better what's happening, even though the velocity field, since I want it to be fairly basic, is kind of a weird one. As x gets bigger, it gets faster. Kind of a weird thing. Same thing for z. So it's kind of a weird velocity field, but the steps work out. So any questions on this? Oh, because the dot product is a constant. And we know that if we do a double integral of a constant, we just get the constant times the area of what we're integrating over. So in some ways, it doesn't vanish. It's just that we don't need to do it because we know we're getting the area, and we know the area of this thing. So in the last one, in some ways, it was similar. It's just that if that had been a constant, we still probably would have to do the integrals because I couldn't picture the thing. So in some ways, as I said, so it's a disk. So for the parameterization, we know we're going to use polar coordinates because it's a disk. That'll be the easiest thing. And therefore, our usual thing would be x is r cosine theta and y is equal to r sine theta. Since it's a disk, r ranges from the origin, so r equals 0 to r equals 5. And theta goes from 0 to 2 pi because we're doing the whole disk. It's just that I wasn't thinking ahead. So when I started writing out the parameterization, I said r is in terms of u and v. So instead of r's and thetas, I have u's and v's. But otherwise, these first two are just the usual polar coordinates. And then z, you can see, is just given. Oh, and so then if we were filling in, I didn't give myself enough room, we would just put in, right, this is x squared, so it's the x quantity squared, so it'd be u squared cosine squared v. Y is xyz, so it'd be the u squared sine v cosine v times 3. So for these two, just plug in the variables in the parameterization. And you can see we don't really want to do it that way because it's starting to get pretty messy. Oh, because this, it's a disk. So 5 would be, which doesn't make sense here, if it was x squared plus y squared is equal to 5. So just the circle. We want the filled in disk. So we want the radius to go all the way from the origin, the center of the disk, all the way to the outside circle. To make it a two-dimensional thing, right? Because if it was just equal and just 5, we'd have just the path, the circle. Okay. Any other questions on this? That I'd have to look at. So I had to take the derivative with respect to u, which is cosine v sine v 0, derivative with respect to v, which is negative u. So I had to look at. Oh, but even if it is, actually, forget about that. So if is the cross product 0, 0, u? But remember, what we're doing is we then need to make it kind of a unit vector. Because when we do the normal, we just need the direction. Although there's a bit of fuzziness there, which you have to think about. Okay, so any other questions on this? So here is, the last one was the direct way where you go through all the steps. This one is one where we can skip some of the steps because we can read off the norm. All right, so let me actually introduce the next section, because like before, it's going to do it in a different way. So what I'll do is I'll again start with the vector velocity field, give you the other way of doing it, and then we can do it this way also. So we'll be able to do one more example, but now doing it two different ways. So this is 4.6. So the divergence theorem says I don't know why it doesn't look like my views. So this is looking like a partial derivative, but that in this form is sometimes the notation for the boundary. So if M is the boundary for a three-dimensional solid, and it'll be easier to see what's going on when we actually do an example, then the flux I shouldn't put that there. So in some ways, probably easier to just read this. This is the notations. So that's what looks like kind of a partial symbol. In this context, that is shorthand for boundary. So if M is the boundary of E, then the flux through the surface M is equal to the triple integral of E through this thing, which came up in 4.1, so let me remind you what that is. It's the divergence of F, which is, if F is the velocity field F1, F2, F3, it's the derivative of the first one with respect to X. And again, I'll make it more explicit when we do an actual one. And then the derivative of the second one with respect to Y, or the third one with respect to Z. So this is somewhat an extension of Green's theorem. So here the idea is, suppose we have a three-dimensional solid, E, and the boundary of that is M, so the two-dimensional surface. So here think of E, let's make it a fairly simple one that we can think of. Suppose E is the solid sphere, so the three-dimensional thing. And in that case, M, the boundary, would be just the shell of the solid sphere, the actual sphere. So it would say that the flow through the sphere is equal to the triple integral over the solid sphere of this divergence. And to tell the truth, I don't have a great intuition of what the divergence, what this thing is giving, so I'm not sure exactly how it works. Well, except when I say generalized, notice it's not quite the same thing, because with Green's theorem we had Q of X minus P of Y, And this is not really, this function is no longer really an extension. So it's sort of an extension, which is, again, the idea is you can take the n-1 dimensional thing on some field and make it into an n dimensional thing on some function of that vector field. But from 2 to 3 dimensions, it's changing what the function is. And as I said, I don't have great intuition of getting that. So I'm sure it does generalize, but it would not be the same function. So as I said, let me do an example. So here's what we're getting. So here's really the idea. And like the other one, there's all the background, which it needs to be fairly nice. So when we talk about the solid E, it can't be in pieces. It can't have corner type things, except for maybe at a couple points. The surface has to be fairly nice also. And since the flow can be in one of two directions, so we do have to be a bit careful, which is that this would be the flow. We'll get that when we do the example, when we do the actual example. So example. I'm not sure why I'm using F. It doesn't really matter, but these are usually velocity things, so I'll only call it V instead. So suppose we have this velocity field. And again, this wording you can see is kind of a weird thing. Let's find the flow through the solid of a cube. So if I'm picturing the river, it doesn't quite make sense anymore, but that's okay. And let's make the cube just all three variables are between 0, say, and 3. So what the divergence theorem says is that what we want, the flow through m of the velocity field is equal to I'm going to use this instead of the notation, although it does make it look a little weird. Because we have the two V's. That's why I used that, because otherwise it looks weird. So V, the second V here is for the volume. The V here is the velocity field. And here, m is equal to the boundary of the cubes, so the 6 sides, and E is the solid cube. And then divergence. So here, this is the F1, F2, F3. It says, or V1, V2, V3, take the derivative, the first one with respect to x. So the derivative of the first one with respect to x is 2x. derivative of the second one with respect to y, so plus 4. And then the derivative of the third one with respect to z, which is plus 1. And then do the typical triple integral of that function over our surface, over our solid. So here, for this first one, I made it nice and simple, which is all three variables just go from 0 to 3. And I would get that. Oh, and I lost a little piece. Here. You have to say which orientation we want. So divergence works if we want the orientation out. If we want the orientation in, the only thing we do is just put a negative sign in front of it. So this is the new part. So similar, as I said, in some ways to Green's theorem, which is we have something, this new thing, this flux, and we get it by getting this thing called the divergence. And as I said, I don't have great intuition of why that works. And we make it now into a typical triple integral from chapter 3, where we integrate the divergence over whatever the region is. Which means we might use rectangular coordinates like we do here, but if the thing was a sphere, so if we're integrating over a sphere, we might want to use spherical coordinates. If we're integrating over a cylinder, we might use cylindrical coordinates, whatever we want to use. Okay. So let's start it the other way, and I might have to go into the next one. Actually, I think I will just go over it. So first, any questions on this before I use this as an example to do another one the basic way? And you'll see why we don't really want to. So let me do this same thing. And in this version, we're just looking at the sides. So the first reason you can see why we're not really going to want to do it this way is we have 6 sides. So what we're going to have to do is do each side separately, add then all 6 sides. So you can see this one's going to be kind of a pain. So let's start with, just to be different from the last example, let's look at the front. The front is where x is equal to 3. So like the last example, we can read off the normal. What is the normal in this case? Here you can see this is going to be a little messy, so we actually will have to kind of do a parameterization, but it is fairly straightforward. So x is, of course, 3. And now the front is just x, y, and z are any numbers between 0 and 3. So I'm just going to let y be u and b be z be b, and now u and v can be any numbers from 0 to 3. So that gives me that square at the front. Okay. So we go through the steps, and you can see this isn't too bad. It's just a pain because we have 6 sides. So we take the partial derivatives, the derivative with respect to, actually, what am I doing? Don't need that. We have normal. We do the parameterization. Which ones do we care about? Right, we just care about the first term. So these two we don't really care about because we know we're going to take the dot product with the normal. So whatever these are doesn't matter. So I just have to put this parameterization in, which is x is 3. So 9 plus 3 times u times v squared. So put in the parameterization. And then we get the 0 to 3, 0 to 3, dot product of this thing, whatever, dotted with the 1, 0, 0. So here we're looking at, so we have the cube. So the first thing is, and when we say the cube, I'm just looking at the sides, because we're looking at the flow through the two-dimensional surface, the sides of the cube. And the nice thing is those are flat. And when we're looking at the front, that is parallel to the YZ plane, which means if I want to get something that is perpendicular to it, it would be along the x-axis, which is 1, 0, 0. And then we take the dot product into the integral. Well, no, so now we keep going. I said, once we start going through it, you'll see that we don't really want to do it this way. Right, so now we have the back, x equals 0. I'll do the front and the back. What would be the normal in this case? Right, just the opposite way. -1, 0, and 0. The parameterization would be the same, except x would be 0. So it would be 0, u, v. Again, u and v between 0 and 3. And then when I plug it in, I'm not sure why I'm using x, the v. The parameterization will be plug in x squared, so 0 plus 3u v squared. And again, we don't care because we're going to be taking the dot product. So in the previous one, we did a disk, right? Just that one disk. So there's only the one piece. Here we're looking at a cube, which has 6 sides. So what we're going to have to do is look at every side by itself. So we look at the front, then the back, then the left side, then the right side, then the bottom, and then the top. So we're going to have to do all 6 sides. as I said, this you can see why we don't really want to do it this way. This is the basic way, as opposed to what we did in the last part, which is we instead use the divergence theorem to make it into a triple integral. Well, so the one, if you mean in the previous slide, this is the exact same problem. So we did, first one I did where we just had a parameterization. I don't know what that looked like, so I just had the one surface. The second one we did a disk, which just had the one surface. And then this is the same as the last part. The last part we rewrote it because divergence theorem says instead of doing on the boundary, we can do the triple integral on the solid. And thank you. So as I'm answering one question, I'm doing other ones. Someone else answered another one. So yeah, so the back would be, because I don't have it on this slide, but remember on the last slide we said it was oriented out. So we're always pointing away from the cube. So we're not pointing in the positive x direction, we're pointing out, moving out from the cube. And you can see I've only done two of the parts. Now we'd have to do this to the left side and the right. For the right side, when y is equal to 3, what would the normal be? So let's actually go through this, because make sure you're okay with this part. Since we have 6, I'm not going to do the whole thing. So let's do sides. So if I look at the side where y equals to 3, then that is parallel to the xz plane, and therefore what is the normal vector? So that's the right side if I'm looking at it from the front. Right, so 0, 1, 0. 0. If I'm looking at it at the left side, y equals 0, what's normal? And again, the reason it's the negative in this case is because, again, we said that we're looking for the flow out of the cube. And so therefore pointing away from the cube. And then we have the top and the bottom. So the top is z equals 3. So that's the top of the cube, so it parallels the xy plane. So in that case, the normal is right. And then the bottom, z equals 0, would be, might as well fill them all in. 0, 0, and -1. And so for each of them, we would plug in the parameterization. So for example, in the sides, the parameterization would be r of u and v would be equal to, in this case, y is fixed, so y would be 3, whereas x and z can be whatever number you want. So I would make that say u and v. And since it's a square, u and v would be between 0 and 3. And then same thing for the left side, it would be u0v. We plug that into the vector, the velocity field, and then take the dot product with normal. And then the same thing for the top and bottom, except now we'd be fixing z. And again, plug it into the velocity field and take the dot product with the normal. And so for this second one, for the sides, since only the middle term is non-zero, we wouldn't care what we get when we plug relation into the first and the third component. You can, it's not going to hurt anything, it's just you're doing a little extra work. So since I started this one, although I do have it in my notes, do you want to continue and get to the the full setup for the integral for the front, the right side? No one's saying anything. So let me do it anyways, because I'm going to ask you, you have it, and I'm using F again for some reason. So go back to the velocity field that we've been using. If I put this parameterization in, what do I get? And I know that the only one that really matters is that middle one. So what is my middle piece? So the original velocity field was x squared plus 3yz squared, and then x squared is z plus 4y, and so on. So yeah, so u squared v plus 4y, which is 12. That's coming from the velocity field from the beginning of the problem. And we could do the same thing for the first and third component, but we don't really need to, because we're then going to take the dot product with n. So we're going to get the double integral from 0 to b, 3 for both of them, and then whatever these are, of those things. And then for the left side, pretty much the same thing, except we would plug in y equals 0 instead of 3, so it would just be u squared b, and this would be a negative instead of a positive. So individually, the sides, all the 6 sides are fairly easy. It's just that there are 6 sides, whereas using the divergence theorem, we could do it all with one triple integral. Okay. So any questions on this? Okay, so let me do another one. This time I'll just use F in the beginning. Oh, sorry. No, so you will only have to do it one way. So here I think, let's see if this is true. Yeah, so you'll see in this one, it'll be strongly hinted that you will do it one way, either use divergence theorem or directly. And I might just tell you use the divergence theorem, for example. So here's our velocity or vector field. So I'll read it in a second. I know my writing here is really pretty bad. So there's our vector field, and we want to find the flow or flux through the upper half of the sphere, radius 2, and closed by putting in the disk at z equals 0, so we have the circle of radius 2 at the bottom. So again, the divergence theorem says this, where here M is just the surface, so the upper half of the sphere and the disk. And here E is the solid half sphere. So the boundary, M is the boundary, E is the solid. So let's try it using the second way. What is the divergence of this function? So again, it is the derivative with you, and here since there are only 3, I'm just going to call it P, Q, and R. Right, so it's just going to be the derivative of P with respect to X, plus the derivative of Q with respect to Y, plus the derivative of R with respect to Z. So 3 plus 1 plus 4. So therefore we get the integral. And this is the solid half sphere of 8 dV. Kind of like in Green's theorem, although here you probably don't know as many of the formulas. Since it's a constant, when I integrate, I'm going to get the volume. So, anyone remember what is the volume of a sphere? Hey, there it is. Almost. Anyone else remember? Right, so the only thing is it's 4/3 pi r cubed. That's for a sphere. Since it's half sphere, what are we going to get? Obviously, just 2/3 or 4/6, right? So 2/3, the pi r here is 2. So I get the 128 over 3 pi. So again, this part comes in because the divergence theorem works if we have that we're looking at the orientation out of the surface. If it was oriented in, all we had to do is put a negative in front. So we could do this the long way. For the sphere, what do you think our parameterization would be? What coordinate system would we use? And there are 2 parts, so we have to break it into 2 parts. So we'd have the disk, and that we would use the polar coordinates. And that would be like the last one where we do x is equal to u cosine of v, or if you want to use r and theta, and y is u sine of v, where u goes from 2, because it's radius 2. And then for the sphere, what coordinate system would we use? So the polar coordinates would give us the the disk, but what about the upper half of the sphere? Right, so we use spherical coordinates. Here it's not solid, so our rho would be 2. We're on just the surface of the sphere, not the whole inside part, not the solid part like we do with the disk. And so the idea is this only works if it's closed. So the first example, it wouldn't have worked because it wasn't closed. The second example, where we're looking at disk, it wouldn't work because it's just one surface. It's not enclosing anything. So this only works is if we have the boundary of a solid. So let me combine this with the last one, which is here we did the flow through the sphere where it's closed by the disk at z equals 0. Let me ask, how would we do it if we did not have the disk at z equals 0? So we just had the upper half of the sphere and it wasn't closed. What could we do? Which I'll write in a second. So similar to Green's theorem, if it's not closed, what can we do? Well, we can add it in, right? We can add in the disk to close it. Then we can use the divergence theorem. And you can see here we really kind of want to, because it's obviously been designed so the divergence is fairly simple. Whereas if we were going to use the parameterization, x we know is the rho sine of phi cosine of theta, where rho is 2. So it would be 2 sine of u cosine of v, and that's what we're putting in for x. For y, it would be the 2 sine of phi sine of u sine of v, and the z would be the 2 cosine of v. And you can see this term especially is going to be messy. We're going to have things like sine of u cosine squared of v in the exponent, which is not going to be nice. So you can see it's been designed not to do it the direct way because you're getting really messy stuff, whereas divergence has been made to be easy. So let's do the next part. 2/3, because the 4/3 is for the full sphere, and we just want the upper half. Okay, so I said that, but let's actually do it. So let's do the same f. So same setup here. So same f, still the upper half of the sphere, but now without the disk. So so I can draw the integrals, let S be the half sphere, d be equal to the disk. So we know from the last one, what do we get? 128 over 3 pi. So we know if we close it with the disk, we get this. So what we want to do is now we want to get what is this for the disk. Which is the disk of radius 2 at z equals 0. And you can see this is now going to be similar to the second one we did of these, because I can read off, and kind of like the last one, I can read off what is the normal we want? And this is the normal for the disk. So what's the normal? Right. And then you have to remember that to make it so the divergence theorem works, we need it out. So 0, 0, negative 1, which means when we put in the parameterization, what's the only term we care about? The last one, right? So this is the only one we care about. So let's go back, and I'm not going to write out the full vector field, but what we had was, so let me write this and then go back. So the vector field we had was something, something for z plus 2. And you can see, again, this was made to do this problem nicely, because when we do the parameterization, to plug in, the only one we need is z. And what's our parameterization for z here? 0, right? So therefore, well, I shouldn't put 0 there. There's nothing there. I don't know what's there. So something, something 2. So I go back to Maxwell's. So here, the first thing you have to remember is here we wanted, and in this case, I'd have to be a bit more specific, because since it's not closed, we can't really talk about oriented out. So what I would have to say is, suppose we have the upper half sphere, and I want to find the flow out through the top, so going up. So if I close it with a disk, since the top is going up, which is now out, we need the bottom to also be out, which means it's going down. So the reason we want it to be 0, 0, negative 1 is because we want to make it so that the flow is out of the half sphere, and out is down from at the bottom. Okay. So we want to do the disk, and we again do the dot product, so that whatever 2 dotted with the 0, 0, negative 1, which gives me the double integral of negative 2. As I said, notice it's been designed that this is nice, because that's a constant, which means I don't actually have to do the integral. And what am I going to multiply the negative 2 by? Right, 4 pi, because we're doing the double integral, so we want the area of the disk. So, since this, I can fill this up here, so this then goes to, so the sum of the two is 128.3 pi. And that's equal to the integral of s, which is what I really want, plus the integral over d. The integral over s is equal to the integral over the sum minus the integral over the disk. And since it's the minus, we get a plus 8 pi. So we're subtracting, which in this case becomes positive because we got that the flow down through the bottom is negative. Okay. So in general, it isn't necessarily easier to do it using the divergence theorem. It's just another way of doing it. So this one was obviously designed to be nice for divergence, but other ones it might not be easier. So here, what we did was we had the upper half of the sphere. And here I didn't write the whole thing. So it was the upper half of the sphere without the closure. So we closed it with the disk at z equals 0. So imagine a half sphere above the table, and we want the flow out of the sphere, half sphere. So when we close it with the bottom, we're pointing straight down. So here's what we have. I can't draw the spheres very well. There's our sphere. And then we close it with the bottom half. And you can see that the normal is pointing straight down because it's pointing out. It's also, the normal is also pointing straight up, but we want the one going out. So first we pictured it, which is it's flat. The disk is flat, so it's easy. We can just have one normal. And so on. And you can see this is quite a bit easier because if we were doing the full way, we would do the parameterization, which is pretty messy for the sphere because it's the spherical coordinates. Then we'd have to take the two partial derivatives, take the cross product, and it's been designed so the function, when we put the parameterization in, isn't nice either. So the whole thing would be pretty messy. Could work out, I don't know. I haven't actually tried it because it looks hard, but it might not be. So as I said, in general, divergence isn't necessarily easier, but we can design it so it's definitely easier like this one. And so obviously we have to do more. So usually I now have you work on one, but we don't have much time. So what you're going to try for tomorrow is look at the homework for 4.5 and 4.6. Obviously, at least half the class tomorrow, hopefully it's obvious, we're just going to be doing more examples of these. And then we'll get into the last thing, 4.7. Because tomorrow is the last class where we do anything new. So today we're actually a little bit short because we didn't have to do the in-class problems. But so we're going to try those. Okay, so the usual thing. So any quick questions? So Thursday, nothing. So the idea is you now have a review for the, well, so two possible things on Thursday. One is you have the review for the test. So we'll go over questions, although you'll have the answers like usual. And then we can also go over homework problems. So nothing new. So let me do the usual thing, at least stop recording.